Hey guys, in this video we're going to prove a few details about basic differentiation. So to begin, let's differentiate the function y of x equals x to the power of n, where n is any positive integer, actually. So we showed last time that if we want to differentiate this thing, we have that y prime of x, the derivative. So remember, the derivative is the gradient of the line tangent to the function at each value of x. So y prime of x is equal to the limit as h tends to 0 of y of x plus h. Well, in this case, y of x plus h is simply x plus h to the power of n. We've put x plus h into here instead of x. So x plus h to the power of n minus y of x, so minus x to the power of n, divided by h, taking the limit as h tends to 0 of that thing. Well, we know from the binomial theorem that when n is a positive number, you can expand that x plus h to the power of n out as follows. So limit as h tends to 0. Now x plus h to the power of n is going to be x to the power of n plus n choose 1, which is n x to the power of n minus 1 times h plus n choose 2 x to the power of n minus 2 h squared plus ... Well, this keeps going all the way up to n choose n, which is 1 h to the power of n. And then we're still, and I've run out of room unfortunately, we're still subtracting x to the power of n. So this is all one line. And we are dividing that by h. So, well, first of all, we can see that these x to the power of n's cancel. And the point is that actually every other term along here, all of these terms, even the ones included in the ... they all have a power of h that is greater than or equal to 2. They all have a power of h that's greater than or equal to 2. So let's go ahead and divide this out. So we still have the limit as h tends to 0. We cancelled off these x to the power of n terms. So what we're left with is n x to the power of n minus 1 times h plus n choose 2 x to the power of n minus 2 h squared plus ... plus n choose n, which is just 1 h to the power of n, and we're dividing that by h. Well, what we're going to do is actually we're going to take away 1 from all of these powers. We're going to take away 1 from all of these powers, except this one is going to cancel off because h divided by h is 1. So what we're left with now is the limit as h tends to 0 of nx to the power of n minus 1 plus n choose 2 x to the power of n minus 2 times h plus all the way up to h to the power of n minus 1. Well, as h gets closer and closer to 0, all of these things are going to get closer and closer to 0. This thing doesn't even depend on h, so that's going to stay fixed. And so what we're going to end up with is actually just all of these things are going to vanish off to 0, and so we're just going to end up with n times x to the power of n minus 1. And so, if y of x is equal to x to the power of n, we have that y prime of x is equal to n times x to the power of n minus 1. And this is called, by the way, this is called the power rule. This is called the power rule, and it actually works for any n that is not 0. For any n that is not 0. Well, actually, I guess it even works for n equals 0. So this actually works for any number n that you can think of. What we showed it was true for was any positive n. Actually, we suppose that n is a positive whole number, but actually this works for any real number n that you want. So that's kind of important. Okay, this is called the power rule. we're going to show a couple of other things now. What we're going to do, we're going to suppose that we've got one function added to another function, and we're going to differentiate that. So let's let y of x equals f of x plus g of x. So y of x equals f of x plus g of x. It's two functions added together. And I want to show that y prime of x is equal to f prime of x plus g prime of x. So that means we don't even need to worry about addition. We can just kind of ignore the addition and differentiate each of them separately. Okay, so let's go ahead and differentiate it. We've got y prime of x is equal to the limit as h tends to 0 of y of x plus h. Well, that is f of x plus h plus g of x plus h minus, well, y of x, which is f of x plus g of x. F of x plus g of x. Oh, but we're minusing f of x plus g of x, and that's actually minusing f of x, then minusing g of x. Because we're minusing the whole thing. We're minusing f of x plus g of x. We're minusing that whole thing. So that's the same as subtracting both of them individually. And this is, of course, divided by h. Well, now you may have observed that we can kind of group them differently. This is equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h plus g of x plus h minus g of x divided by h. And assuming that this thing gets closer and closer to some number as h gets closer and closer to 0, and this thing gets closer and closer to some number as h gets closer and closer to 0, well then whatever number the whole thing gets closer and closer towards must be the sum of those two numbers. And so in fact this is indeed equal to, let me write it out again, this is indeed equal to limit as h tends to 0 of f of x plus h minus f of x divided by h plus the limit as h tends to 0 of g of x plus h minus g of x divided by h. And so this is indeed equal to f prime of x plus g prime of x. So, well, that's great, because that means that this thing is true. Oops, not this thing. Where is it? Here. That means that this thing here is true. So whenever you've got y of x equals f of x plus g of x, if you differentiate that, then it should be the derivatives of the two functions that y is the sum of. So that's a very important thing. That means we can just kind of ignore the addition. We can ignore the addition. So far, we know this. We know this, that whenever you've got x to the power of n, the derivative of it is y prime of x equals nx to the n minus 1. We know that. And we now know that we can ignore addition. One more thing we should show is that, we can also ignore multiplication. So let's let y of x equals k, where k is some number, times f of x. Then I want to show that, well, let's just find out what the derivative of this thing is equal to. So the derivative of this thing, y prime of x, is equal to the limit as h gets closer and closer to 0 of y of x plus h, so k times f of x plus h, minus y of x, so minus k times f of x, divided by h. Well, let's bring that k out. This is equal to the limit as h gets closer and closer to 0 of k times f of x plus h minus f of x, and then that whole thing divided by h. Well, now, if this thing here in the red circle gets closer and closer to some number as h gets closer and closer to 0, well then k times that thing must get closer and closer to k times whatever that number is. That's, I mean, I don't want to say common sense, it's because it's kind of a deep idea, but I mean, let's just take it as a fact for now. So this must be equal to k times the limit as h gets closer and closer to 0 of this thing, of f of x plus h minus f of x divided by h. And so that's equal to k times f prime of x. So y prime of x is equal to k times f prime of x. So if we're multiplying by k at the front of a function, when we differentiate it, that k just hangs out there. That k just stays right where it is. It's so the derivative of k times f of x is equal to k times the derivative of f of x. We can just leave that that k right where it is. Okay, let's list our rules. So let's list what we've learned today. We know that if y of x equals x to the power of n, then y prime of x equals n times x to the power of n minus 1. We learned that if, so this is, I guess, number 1, the first thing we learned. The second thing we learned, use a different color just for fun. Second thing we learned is that if y of x equals f of x plus g of x, then y prime of x is equal to f prime of x plus g prime of x, assuming these things can be differentiated. And the third thing we learned is that if y of x is equal to k times f of x, then y prime of x is equal to k times f prime of x. So we can ignore the addition sign. The addition sign just hangs out right where it is. And we can ignore the multiplication. That just hangs out where it is as well. So we can put a couple of these things together now. So using rules number 1 and rule number 3, say, so using this one here and this one here, we know that if y of x is equal to 3 times x to the power of 100, then that tells us that y prime of x is equal to 3 times 100 times x to the power of 100 minus 1. 300 x to the power of 100 minus 1, so x to the power of, that's a horrible 9, x to the power of 99. So in our example, this one here is the f of x, and this one here is the k. This 3 is the k. So that k is the 3. That x to the power of 100 is the f of x. And we used rule number 1 to differentiate our f of x equals x to the power of 100. And we can now use rule number 2, which says we can ignore addition, to actually differentiate any polynomial we want. So let's say we got y of x equals 2x squared plus 3x to the 4. Then I know immediately that I can ignore addition, and y prime of x is equal to 2 times 2, x to the power of 1, so 4x to the power of 1, that's just 4x, plus 3 times 4, x to the power of 4 minus 1, so 12x to the power of 3. Done. Nice and easy. Very quick. Okay, well that's all well and good. I forgot to do a couple of examples, didn't I? What about x to the power of 1? How do we differentiate that? So let's let y of x equals, say, just x, x to the power of 1. What is y prime of x? Y prime of x, well, again, so x to the power of 1, we bring the 1 down. So y prime of x is equal to 1 times x to the power of 1 minus 1. So that's 1 times x to the power of 0. So 1x to the power of 0, and that's just equal to 1, because anything to the power of 0 is 1. And so 1 times 1 is 1. So whenever you've got x to the power of 1, it's when you differentiate it, it's just a constant. So using that, we can now say that for y of x equals, I don't know, 6x, then y prime of x, I can leave the constant out the front alone. I can leave that 6 alone. Y prime of x is just equal to 6 times 1, which is equal to 6. Almost done. Got to do one more example. The last example is the following. Y of x equals 3. That's just a constant. In fact, I don't even need to write 3. I can just write k, any constant k. What happens when you differentiate this thing? Well, k is actually equal to k times x to the power of 0, because x to the power of 0 is 1. And we do exactly what we're doing before. We can bring this 0 down, so not equals, y prime of x equals, we bring the 0 down, so 0 times k times x to the negative 1, well, 0 times anything is just 0. So if y of x is equal to some constant number k, when we differentiate y prime of x is equal to 0. So when you differentiate a constant, you get 0. Okay, that's it for now. Thanks very much for watching. Hope it was useful. See you soon. Bye.